it deals a lot with lines. But we're going to do, normally when you think of lines, you think of a two-dimensional space. Y equals mx plus b. You can also draw lines in three-dimensional spaces. Right? If an airplane flies from one place to another, it has to follow a curve, but it's in a three-dimensional plane, so now there's more than just x's and y's. And then we can move on to other dimensions as well. So linear algebra deals with lines in a bunch of different places. Here is our basic system of lines that you've done before. Y equals mx plus b, or you could rearrange it so you have a 0 on one side. I'll just finish up attendance here. So we used to have this. Do you remember two equations, two unknowns? Of course you did. It comes up a fair bit in solving stuff. Whenever you had two things you didn't know, you knew that you needed to have two equations to solve it. Both of these are lines. Both of them are y equals mx plus b. And if those two lines have different slopes, they will cross somewhere. So we learned way back in grade 10 and grade 11 different techniques for this. If I was looking at this one, I would probably be tempted to do the substitution technique. It's really easy to get that x by itself. And then once I have that x by itself, that's equation 1, I can plug it into equation 2. So the x I replace with 6 minus 4y minus 3y plus 1 equals 0. And now I have an equation just with y's. So if I multiply this out, (12 plus 1 is 13, negative 11y equals negative 13. Not a great number, but I can solve for y. And if I solve for y, now I could plug it back in. I could plug it back in and find x. Something you noticed? No. All right. So we call these a system of equations. Graphically, the two graphs where they intersect is the solution. It's the point of intersection. Okay, so we're going to be extending this not only with 2 dimensions, you can have 3-dimensional lines intersect eventually, and we're going to learn matrices as a technique for solving systems of equations. So something you already know how to do, we're going to learn to do it in a totally new way as well. So there's 3 types. You have this type with one solution. This is called an independent system. If 2 lines in 2 dimensions have different slopes, they will obviously intersect at some point somewhere. Technically they're y-intercept. This part I could put just different slopes. You could have the one point where they intersect happen to be the y-intercept, right? So they don't need different y-intercepts. They just need different slopes. Next, we've got a dependent system. A dependent system, you have an infinite amount of solutions. In fact, they are exactly the same line. And this could be written like this. I have one equation that's x equals y. And my other equation will look like this, 2x minus 2y equals 0. And you're asked to solve. And you're like, ooh, I can use substitution right away, right? I could just plug in, instead of the x, I could plug in a y. And then I get, something weird happens algebraically. And this is often what happens with the dependent system. You're going about solving it, and you find out that 0 is equal to 0. Sometimes 5 equals 5. 3 equals 3. And you're like, but I haven't figured out what y is. Number one mistake students then go is like, I got a bunch of zeros, so I guess y is 0. And then x is 0. Well, that's true. That's one of the solutions, but that anytime you get something that's always true, if it's always true, it means it works all the time. There's an infinite amount. Well, it doesn't work all the time because obviously the point 3, 2 isn't a solution to this because the x and the y have to be the same. But there are an infinite amount of places where x is equal to what? 3, 3, 4, 4, 5, 5. Pi. So there's an infinite amount of correct solutions. This is called a dependent system. And you have exactly the same line. They're going to have the same slope. They're going to have the same y-intercept. And if you try to solve it with substitution or elimination, you will get something like 0 equals 0, which is problematic. And then you have your incompatible system, 2 parallel lines. Y equals x plus 1, y equals x plus 3. Those have the same slope of 1. One has a y-intercept of 1, one has a y-intercept of 3. Now, if you didn't notice, because sometimes these get mixed up, that you don't see that the slopes are the same right away and have different y-intercept. And if you used substitution here, and I substituted x plus 1 in for that y, and I subtract x on both sides, you get things like this. You're like, 1 is equal to 3. Well, that's obviously not true. If you believe it's true, give me $3. I'll give you $1 back. We'll be even. All good. But yeah, 1 is not equal to 3. Unless we've got units and there's some sort of weird conversion. So this is an incompatible system. There would be no solution. Obviously, this is never true, meaning that you have no solution. So a review of the techniques that we've had in the past to solve this. We already did substitution. Do you remember your elimination technique? And of course, the graphing technique is nice if you have Desmos or your graphing calculator, because then you can get your answer really quite easily and quickly. But graphing it by hand without a calculator is never a good strategic option. So if I was solving this one, I've got my equation 1, I've got my equation 2, I would substitute in. Never substitute back into the same equation. That'll never work for you. It's the one thing that if you end up getting 0 equals 0 or 5 equals 5, and you're like, oh, it's an infinite amount of solutions. Just double check that you didn't plug it back into the same equation. Because I've seen students who have to do some work to get x by itself. It's not easy, right? This one was pretty easy, just had to move the 2y over. But then they accidentally took that x and substituted it back into the same equation. And if you take the same equation and plug it into the same equation, does it make sense that you would have an infinite amount of solutions? They're the same line. So with substitution, we have to make sure that we're substituting into the other system. And this one happens to be 0, 0 anyways, which is always true. If you use the elimination technique, what you want to do is you want to have all of your columns, when you write them, line up to be the same thing. So I had my x's first, then my y's, then my numbers. And as long as things match up that way, the next thing you're going to want to do is get the coefficient in front of one of them to be the same. I like to have one positive, one negative, because then I can add. If they're both positive, you could subtract equations, but students make more mistakes when subtracting than when adding. For those of you that like to make tons of little mental math mistakes, I'll warn you, this unit might drive you crazy. Because we will get questions that just like a typical question will require 50 small mental math calculations. Usually ones that are so easy that you could do them in your sleep. But sometimes when we're sleeping, we make mistakes doing things we should. Like 1 + 1 is 1. 3 × 2 is 5. Those things happen quite a bit. So be careful in this unit because we're going to do lots of easy mental math that can cause your brain to hurt. All right, so we'll do that one more together. This one, if I'm looking at it, one of the things you're going to want to do is you're going to want to decide, do I want to use the substitution method or the elimination method or graph these? Okay, usually graphing I don't even mention as an option. Unless you have a calculator, then this is going to be great. Okay? Desmos would be perfect because you don't even have to rearrange. Graphing calculator, you'd have to get y by itself, right? Desmos, you could write it in just like this. Boom, get an answer. How many people use Desmos on their exam? So if you wanted to get a variable by itself, like I chose to get the x by itself in equation 1, I get a fraction of 4/3. I could plug that into the equation. It's just dealing with fractions, which isn't the hardest thing, more annoying than anything. And I could rearrange and solve, and y actually turns out to a nice number, -3. Once you've got your y value, then it's just a matter of plugging that into either of your equations to get your x value. And often we write our solution as a point, because that's what happens with a system of equations. You've got an x and a y. Your solution is a point, 2, -3. If it's using different letters like m and n, then we just usually write m = 2, n = 3, that way. So because I would have noticed, for me personally, because in this one I would have looked at this and said there is no variable that's easy to get by itself in either equation. No matter which variable I get by itself, I know that I'm going to have at least one fraction, maybe more. In this situation, I would probably lean towards the elimination technique and go, I could take equation 1, and you see what I did? I took equation 1, I multiplied it by 2, and I took equation 2 and I multiplied it by 3. That got my numbers in front of the x to be the same with one positive and one negative. No fractions at this moment. Now I add those two equations together and I still have no fractions. And look how much easier it was to get y = -3. Once I got -3, I could plug that just the same as on the left. Plug that into the other side. And we get the value of x. So these are review questions. They're not super hard. However, you could get questions like this that say, determine a value of k such that the following has no solution. So no solution would mean that those lines would need the same slope. That's one thing you could take from this. No solution would mean that when you add the equations, you would get something like 5 = 3. If I rearrange equation 1 to y = mx plus b, then this part here is the slope of that equation. And if I arrange equation 2, y = mx plus b, then that part would be my slope. The y-intercept actually doesn't matter whatsoever. So if I want no solution, I need, well, the y-intercept could come into effect. I'll talk about it just a tiny little bit at the end. But if I make those two red boxes the same, and I solve for this, I get k is plus or minus 1. What would be fascinating in this question is that when I said the y-intercept doesn't matter, it mostly doesn't matter. However, if you plug this k into here and these two y-intercepts happen to be the same, then they would be the same line, right? And you would have infinite solutions. So I do have to check to make sure that neither of those plugged in would give me infinite solutions. So if I really wanted to make this the most complicated possible, if I had made this number here originally a 2, then the +1 answer you'd have to cancel out. Because the +1 answer would actually make both equations the same. And you'd have infinite solutions. The -1 answer is the only one that would make them different. But I didn't. Both of those work. So we can ignore that. There's equation 1. There's equation 2. First thing I would do is I would get rid of my fractions. If you got fractions like this, can you see that you could multiply this whole side by 6 and this whole side by 6? Why did I choose 6? Well, 6 would get rid of the 2 and 6 would get rid of the 3. Or I've seen people do, instead of getting rid of the 6's, another common strategy, which I actually quite like, is get a common denominator between everything. So if the common denominator would be 6, can you see that you would have 3x minus 3 over 6 plus 2y plus 4 over 6 and 24 over 6. And if every fraction has the common denominator of 6, now when you multiply by 6, it just has the effect of getting rid of all those 6's, and you get the same thing. Sometimes that's a nice visual step in between, rather than just multiplying by 6 and trying to go, okay, the 6 cancels out with the 2, and then that becomes 3, and I have to distribute. You could easily get lost in some little mental math. This is where I said mental math can come back and bite you. One little negative miss, one little forget to distribute, and your whole equation from then on is wrong. So then you can combine your like terms, and you get 3x plus 2y equals 23. If I was doing this example, I would use elimination, because look, do you see that your y's already have the same coefficient, one positive, one negative? And you get x equals 7. If x is 7 and you plug it in, you get y equals 1. And we have our solution. Majority of questions you've had with systems of equations have been two systems with two unknowns. If you have three things you do not know, then you need three equations to solve it. And this is going to lead into matrices, because matrices work really well when you get bigger and bigger systems of things. 4 equations, 4 unknowns. 7 equations, you would need 7 things. 7 things you don't know, you would need 7 equations to solve it. So what you did back in grade 11, when you had 3 equations and 3 unknowns, you took equations 1, 2, and 3, used a bunch of elimination actually, and the first thing you decided is you were going to eliminate one of your 3 variables, either the x, the y, or the z. And I like equation 1 and 2. Do you see if I add equation 1 and 2 together, that eliminates the x right away. So just noticing that, I made the decision, I want to eliminate the x. If I do that with equation 1 and 2, I get a new equation which, see how I'm labeling equation 1, 2, and 3? My new equation I'm labeling as equation A. I have to take 2 other lines, so I took 2 and 3. And equation 2, do you see that I doubled everything so that my numbers in front of the x's were the same number, different sign? I added those equations together, and I got equation B. Can you see that equation A and equation B both don't have x's? And as a result, now I could use elimination again with A and B, and I have to decide, do I want to get rid of the y's or get rid of the z's? And looking at the numbers, it makes sense to get rid of the y's. I like to add, so I took equation B and I multiplied everything by a negative. Now when I add those equations, I get negative 2z is equal to negative 4. So I know that z is 2. Once I have z as 2, I could plug that z as 2 into either A or B and find out what y is. And once I have y and z, I could plug it into equation 1, 2, or 3 and find x. I decided to plug it into 2 because 2 was really simple. And I got x equals 1. So my solution as a point is 1, negative 1, 2. This example is an example of 3 lines in 3 dimensions. I'd like to get like some holographic kind of teaching tool that I could just like draw lines in 3 dimensions and show that they intersect. That'd be really cool. We just have to use our imagination, and then that's still really cool.